Now let's take a look at example number 2. I want to find the volume of the solid that's obtained by rotating the region that exists between these curves that are given here, but I'm going to rotate it about the line or around the line y equals 1. Now, much like what we did in the last video, I'm going to suggest that we always attempt to draw two pictures here. And my first picture is just going to be of the given region. Now, notice that here, since x is starting at 1 and going over to 4, I don't really need much of the negative x-axis. I'm just going to imagine here that I'm going from 1 to 4. And I'm going to sketch out then my square root function, which I know looks something like this. So this is my y equals square root of x. And I'm going to have a line y equals 1. Notice that my line y equals 1, if I'm careful here, is going to go right through this point. There's my line y equals 1. I know that, of course, the square root of 1 is 1, and so this point is a nice point of intersection. I also have my line of x is equal to 4, which is going to extend like this, and so I should ultimately end up with a region that looks like this space right in here. Now our goal again is to create a volume out of that region by revolving that region about the line y equals 1. So our goal is to take that and spin it around this particular line. All right, so I'm going to go ahead now and create a second picture where I can go ahead and actually draw the 3D solid. Now I always like to, when I draw these pictures, I like to try to take the line that I'm rotating around, if it's not already the x or the y axis, and I like to kind of make it dashed, just so it's easy to see that's what I'm going to be, again, spinning around. I'm also going to go ahead then and just try to generate roughly what the bounds of my blue region are. I don't need too much of it. In fact, I'm not even going to put in this vertical side right here, because that'll kind of just mess with my picture of the solid. But I have something kind of like this. Hopefully you can see kind of the mirror or the duplicate of what I have over there. Now, if I was to go ahead and rotate this around, remember that one thing that I'm going to need is the mirror image of this on the other side of my axis of rotation, or what I'm rotating around. And then I can play a game of connect the dots. I'm going to find a point, its mirror image on the other side, and imagine pulling that point around the axis, and then I do a dashed line when I go back in. And I can do the same thing a couple of times on here to get a good sense of what this solid looks like. So here I'll just do it 3 times again so I can get a sense of these cross sections. Now, it may take a little bit of time for you to get used to drawing pictures like these and to draw them quickly, but I assure you it is very important that you possess this skill. It does take time and practice, but if you skip these steps, it is so incredibly hard to ultimately derive an integral that's going to represent the volume of these solids. Okay, so now I know that this is the solid that I'm working with, and I can already kind of see the cross sections. It seems like I'm going to have this circular shape again, but I should recognize not every circle is the same size. I'm going to ask that every time you see one of these circles, you go to every single circle and you draw in the radius for your circles. Notice that I'm drawing in my radius as it goes back to my original functions. So you can almost kind of imagine that I've drawn in like red lines that are almost like here in the original picture. These are my different radii that I've sketched out. And it's very important that you draw those radii, because remember, I need to find the length of those radii if I want to find the area for the cross section. So it's pretty easy then to see here that the area of each cross section is given by, and I can state, well, the area is going to depend on what x I'm at. If I'm on the left, I have a small area. If I'm on the right, I have a big area. And I know, again, I'm going to use the formula pi r squared because I have circles. If I had a different shape, I, of course, would use a completely different formula. But here, again, I need to go ahead and replace that r with something, because not every circle has the same radius. So again, to measure the length of those radii, I notice that they're just vertical line segments. So I'm going to say if I knew the y value for the top point and I knew the y value for the bottom point, I could just simply subtract them, right? If this point up here was at height 5 and this point down here was at 1, then I know that radius has length 4. So of course, what we're going to be able to establish here is that the top side for each one of those radii is bound or determined by this function square root of x. However, the bottom side is really easy. The bottom y-coordinate for each one of these radii is always 1. And so square root x minus 1 represents the length of every radius. And so I can then go ahead and arrive at a volume. I can have here pi times my radius squared. That's my area of my cross-section. I'm going to give it a little bit of thickness. With my delta x, I'll transform that to dx in the integral notation. And now I'll just say add up all those individual volumes. The integral will take the limit of that and shoot the number of pieces off to forever, and I just have to state my bounds. Where do my circles start and stop? How far left and how far right do they go? If I look back at my previous picture, I'll see that at the very left I'm at x value 1, and I can go all the way over to x value 4. So again, I have a nice integral setup here. And in this video, I'm not going to go ahead and evaluate that. I'll leave that for you to try on your own, since it is just a repeat of a lot of Calc 1 skills. But if you do try this, hopefully you should be able to confirm you get down to a final answer of 7 pi over 6. In the next video, we'll take a look at example 3 and see how we can do the same process again, but with one slight twist.